तिरियो तुझे ठीक ना हो कन्नड़ो नोटिफिकेशन तुझे आवाज दे नहीं
ये पीएससी पे है। अच्छा जी, मैं फिर बोल रहा हूँ हेलो टेस्ट 1 2 3। अगर किसी को मेरी आवाज नहीं जा रही तो काइंडली बता दें। अभी 5 मिनट है हमारे पास वेबिनार स्टार्ट करने के लिए। ये कौन सा आप है? जी हबीब मेमन साहब, आपकी वीडियो नहीं आ रही। काइंडली जिन लोगों ने रजिस्ट्रेशन कराई हुई है उनकी वीडियो लाजमी है। वीडियो देखे बगैर अटेंडेंस नहीं लगेगी। All participants who have registered for this webinar are reminded that their attendance will not be marked until or unless we see their video. This is the rule which has been prescribed by Pakistan Engineering Council. Thank you, sir. जी जिलानी साहब, आपने हैंड रेज किया हुआ है तो काइंडली आप टेक्स्ट कर दें। फिलहाल अगर कोई प्रॉब्लम है तो मुझे इशू है तो मुझे बताएं, टेक्स्ट करें। मुस्तफा जिलानी साहब। अब आया? ये तो नहीं है। ये जी मुस्तफा जिलानी साहब, आप हैं वीडियो पे हैं, ठीक है। हबीब मेमन साहब भी हैं, ठीक है। आप लगा Mr. Saad Tanveer, we cannot see your video. Then we have Muhammad Munib Tariq, Muhammad Ehsan, We cannot see your video. प्रिया को फोन करो भाई, 2 बज गए हैं, 2 बज के 1 आया नहीं अभी तक। असद इकबाल साहब, we cannot see your video. Kindly switch on your video, please. Thank you, Asad Saab. Now we can see you. क्या कहता है? जी जी, 2:03 हो गए हैं। हम स्पीकर का वेट कर रहे हैं कि वो आ जाएं, तो फिर इंशाल्लाह शुरू करते हैं। उनको रिमाइंड भी किया फोन पे, वो आ रहे हैं। सो ही इज ट्राइंग टू कनेक्ट। जी इंशाल्लाह ताला विद इन 5 मिनट्स हम शुरू करते हैं। कुछ पार्टिसिपेंट्स ज्वाइन कर रहे हैं, तो मैं चाहता हूं कि मैं रूल्स एक ही दफा बताऊं, तो इंशाल्लाह 5 मिनट जरा बियर कर लें। हमारे स्पीकर साहब को कोई प्रॉब्लम हो रही है? अभी 3-4 दिन पहले हमने रिहर्सल की थी, सारों ने अच्छी तरह ज्वाइन कर लिया था इंक्लूडिंग द स्पीकर। आज आई डोंट नो क्या मसला उनके साथ हो गया है। तो मैसेज में देखी जाना था। उसे को रीबूट करें दोबारा। जी टीपू साहब, आप कुछ कहना चाह रहे हैं? आपका हाथ रेज्ड है, योर हैंड इज रेज्ड। नहीं, बंद करे सारा कुछ दोबारा। हाँ, सीधा सीधा जो लिंक भेजा उसको, लिंक को कनेक्ट करो। सारी दुनिया ने कनेक्ट कर लिया, आपसे क्यों नहीं हो रहा?
हाँ यूनिवर्सल है अच्छा जी
Bismillah ar-Rahman ar-Rahim. Now we are going to start the proceedings formally. Still, we are having problem with the speaker. He is unable to join, but my staff here is guiding him uh, how he has to join the Zoom. He's being given certain instructions. Let's hope he will join soon. I will In the meantime, I will just give his introduction, and first I will give you the rules that how this webinar is going to proceed. As you know, my name is Tahir Sultan. I represent Pakistan Society of Civil Engineers here, and I am also the moderator for today's proceedings. Welcome to all of you for joining this webinar, which PSCE is holding first time. And as you know, this is because of the COVID-19 problem, which has brought the whole world to a standstill. Since we thought education has to carried on, and it should not stop at the education must carry on. Therefore, after discussion with my colleagues, we decided to start holding the CPD lectures from through the webinar. Now, how long this practice will continue, this is not knowable at this moment because of the COVID-19. Nobody knows when it is going to be eradicated or when the situation will be conducive for holding congregations and gatherings. So, uh, uh, till the prevailing situation continues, we will be holding seminars regularly on webinar, and according to the new schedule, which will be announced on our website and Facebook page. Well, today's rules for this webinar are as follows. First, I will introduce the speaker to you and the topic, and when the speaker will start delivering his lecture, the microphones will remain in the mute position for all the participants. One. Second, I have talked to the speaker, and he is preferring that questions should be asked during the lecture. He has permitted the participants to ask the questions during the while he's delivering the lecture. So the best thing would be that you people text your questions, and the text should be open on the board, no private texting, please. If any participant has any communication issue with the voice or with the picture or any other issue, he can privately text me his message. And later on, once the lecture is finished, then I will give you some news about PSC, the updates, and the procedure how you will get the CPD certificates. Now, still I don't see the speaker joining us, and so I take this opportunity to save the time to introduce the speaker to you. Today is lecture number 17. Our guest speaker is Engineer Sohail Kibriya. that he is going to deliberate on landslide study, analysis, and mitigation. Suhail Kibria is an eminent geotechnical engineer. On the academic side, he did his undergrads from UET in 1980. Then he did his graduation, that is master's, in 2004 from University of Engineering and Technology, Lahore, same university. And apart from his formal engineering education, he has studied in LUMS, Lahore also, and he has got some handful of diplomas, and most probably these diplomas are on for the management, learning of the management. And apart from these LUMS study, he has also been abroad for training and attending some workshops. And the countries he has gone for this purpose are Malaysia, South Korea, Nepal, UK, France, UAE, and Oman. The speaker has, mashallah, an experience of 40 years to date, and mostly his career is with NASPAC, where he joined the organization at the lowest level, that is the junior engineer, and then he rose up to the position of vice president, from where he retired in November 2017. And now today, he's still serving NASPAC on contract basis, and he is the head of research and development there. During his career, he has gained diversified engineering experience related to diversified disciplines, that is nuclear plants, irrigation, highways, hydraulics, dams, you name anything, airports. He has the experience of geotechnical engineering. And during his professional career, he has also worked for some time on let's say on some temporary basis in 9 countries where he has experienced the geotechnical engineering. I think the countries are the same which have already described to you: Malaysia, South Korea, Nepal. That is in Europe, Asia, and Africa. He has worked. His areas of interest, typical interests, are soil dynamics, ground improvement, foundation engineering, and landslides. He has, to his credit, 60 publication of 60 research papers. And mashallah, he is today, he will be joining us soon, I think now. I hope his problem is resolved. So hopefully, as I can hear from the voice of my colleagues, that the problem has been, looks like resolved, and he is going to join us soon. Now again, taking advantage of the time, I will brief you that the next lecture is on 16th June 2020, same time, on webinar, and it will be delivered by engineer Rizwan Mirza, and the topic is earthquake resistant design of RCC buildings. It's an overview for the practicing structural engineers. Now this is something which I had to say as an introduction. Now I have nothing to say except to wait for the speaker to join. He is on his way now, I think. I don't have his. He has been added. Speaker has been added already. He is there. Hanji, Suhail Kibria Saab, can you hear us?
Yeah, I can hear you. Yeah.
Okay, thanks God, you finally made it. I have, during your absence, just to save time, I have already given your introduction, and I have also explained to our participants the rules which they have to follow today during your lecture. I have informed them that they can ask you questions during the lecture, and the method of asking the question would be text, the text messages. The text messages will appear on the board. In case you miss the text, I will, inshallah, remind you that what questions are being asked. So the floor is yours. Please start your lecture.
Okay, thank you very much. First of all, I'm extremely sorry. There was some issue with the connecting system. Anyway, I'm there now. And thanks, Taisa, for your words, which I have not heard, but I feel that you would have said very nice words. Uh, I'll be deliberating upon the very less talked about but very important topic of landslides. What landslides are, how they are studied, how their analysis is carried out for engineering purposes, and how appropriate mitigative measures are designed. So it is very important also from this point of view that the northern part of our country is having rampant landslide issue in different kinds of formations. There are hard rocks, there are soft rocks, and there are a variety of ambient conditions which generate and trigger landslides from one location to the other location. Before going into the actual lecture, I'll first share a video clip which is 5 minutes long, which will show you different types of landslides recorded by camera. I just a minute. Can you see this, please? Please let me know, Tahir. Is this visible on the screen? Hello.
Gigi, have you shared the screen?
Can you see the images, the video?
Oh, we cannot see it.
Hello. You cannot.
Cannot.
I see. So this means it is not working. I will stop it. Okay. If it is, I've shared it, but since it is not working, so I will stop it.
Okay. Go ahead.
Okay. I'll proceed with the main lecture. Okay. Let's leave it.
You have to click on the share screen button.
Yeah.
Yeah, the sharing has started. Please proceed.
Just started. Okay. Let me make it full screen. Bismillahirrahmanirrahim. I think it is visible.
Yes.
So, study, analysis, and mitigation of landslides. I'll be emphasizing on all three parts of the landslide which are involved in the landslide study. And main contents of this talk would be, I'll be giving a general background about the landslides, how to identify on the basis of visual inspection, what kind of investigations and studies, whether at site, in the laboratory, or in the office, are carried out, what kind of analysis are to be done, and what are the mitigative measures, and with some case histories. Can you see the whole, slide on the screen clearly? And can you hear
Yes,
me properly?
we can hear you very clearly and we can see the slides very well.
Okay. In my understanding and in my experience, I would like to share that landslide study and landslide engineering has been one of the most challenging topics in civil engineering. It is the character of the sloping ground where landsliding will take place, and there are a variety of landslides which take place. In a nutshell, I would like to say that landsliding is quite similar to that analogy which we all studied at school in physics class, in which there used to be a slope and a sliding block, and there used to be one particular angle of slope at which the sliding will commence. If the angle is flatter, sliding will not take place, and if the angle is steep, sliding will take place. So, very briefly speaking, it is the characteristic of a sloping ground when we have material movement on a slope. It could be due to increase in the destabilizing forces or due to decrease in the resisting forces, increase in the destabilizing forces or decrease in the resisting forces, it can trigger landslide. There could be various factors behind. And when we have to talk of landslide, there is not one solution which can be applied to tackle and to control all types of landslides. We have to look for the cause, as a doctor would look for the cause of the disease in the patient, that what is the underlying reason. Only then he'll be able to prescribe the right medicine. So even when we have understood the cause, many comparable solutions are available. No, there is not a single solution, and there are different elements involved: the cost, impact, its durability, the ease of construction, etc. Now, going back that simple inclined plane analogy, here you see inclined plane inclined at an angle of theta. We have a block lying over it. Weight of the block is W, and you see it has the weight has two components: one normal to the plane, other tangential to the plane. This tangential component tends to give sliding force, and this one produces some resistance. In soils, the resistance here, it is composed of the force normal to the plane. In soils, we have some additional component because of the cohesion in soils also. The soils which are cohesive, they also take part. And in a nutshell, we call the interplay of cohesion and angle of internal friction as a shearing resistance. So basically, what happens if we make this angle flatter, the block will assume stability. But if we make the angle steeper, an angle will come, a stage would come when the block would start sliding. So this means there is a specific value of angle of internal friction. In soils terminology, angle of internal friction, or here the angle of friction. So here you can see that the angle of internal friction which we typically use for granular soils is primarily, when we talk of a sloping ground, is the angle of the slope. It is basically the angle at which the sliding takes place, this angle, and the same angle is constituted between the vertical vector of the weight and the vector which is normal to the sliding plane, the same angle theta. So this is the angle of internal friction. So sliding is a function of block plane materials, the material which it is composed of, and this one, and the slope angle. So in terms of soils and rocks, the material of soils and rocks will matter, and the slope angle will matter. So in addition, there will be some additional factors like moisture, etc., which will increase or facilitate the sliding process. Here you see in this slide general anatomy, just to share with you that here we have we can see a slide here having taken place in a mountain. The mass has slid all the way down, and here where it originated from, the vertical face of the crack is called headscarp, and when the material moves down, it moves towards what we call toe. This is head and this is toe. And when the material moves towards toe, there is accumulation of the material or heaving of the ground. Hence, it is also called zone of accumulation at the toe, at the base. It's a zone of accumulation, and you can see here a road for comparison. It has been buried. And once a slide has taken place, there are secondary small effects of sliding to regain further stability. So you can see small movements, you see subsequent movements. Here, I would like to share with you different types of common slides which are taking place. Here in the background, you see a rock slide in which rock material slides down. It's the rock material itself. Here, during road construction, this is road because of some unscrupulous practice. Sliding has taken place. Here you can see sliding in this soil mass here. The river bank has collapsed, and here, this is water body, and below water, uh, you see sliding has initiated. Here also you can see erosion of a cliff. So falling of a rock almost vertically, which is called rockfall, is also a type of sliding. If rock particles, while falling, they turn a bit, then it will be a slightly different kind of fall. And here you see debris, uh, debris flow in which the moisture content is fairly high. It could contain coarse particles or finer material or a combination of the two. It is possible in both cases, but the moisture has to be very high. So having seen different kinds of slides, how do we see physically, how do we identify an area if you go to a hilly area? What are the prominent signs one can see to find out whether this is a moving, unstable, sliding, creeping area or not? I think all of you have happened to go to Murray-like area, Kohala, Azad Kashmir, and to Karakoram Highway. So I'm sharing with you some sign that this kind of formation of headscarps, some sliding down on the top, and there could be some low-lying area generated in between on which rain would fall and will get ponded up, resulting to more vegetation. Here, some dried trees you can see. There could be tilted trees also because of the movement, and sometimes when cracks are there in the ground, water drains. It doesn't reach the roots effectively, and trees start getting dried in landslide area. So that's why we see that when the area is relatively barren and with less vegetation, so it has to be understood that in this piece of land, in this mountain, this is probably moving area. If some structures are there, some inhabitations are there, there could be a variety of cracks depending on the type of movement. And here you see a transmission line tower. They have been tilted irregularly. And here you see a sign of a secondary slump. Here you see badly damaged road because of movement. And if there's a fence moving like this, it will also become a kind of irregular in shape. So these slidings have taken place presumably along some surfaces. Sometimes it so happens that a slide took place at a site in the past and now it is almost stable. So these areas are called dormant landslide areas, and one has to identify for important projects, for important situations, whether the area is a dormant landslide area or not. So here you see rock, the soil material, alluvium or colluvium above it. This is called regolith. Technically, this is called regolith, the slip plains, etc. So this is a very brief summary of how we can identify slides at the site. In this slide, you see a disaster which happened back in 2010 uh, at Attabad. You see, huge clouds of dust were formed due to landsliding in the Hunza River, and the river was literally blocked, resulting into formation of a lake, a big lake. Later, some sliding also took place in 2019. This was in 2010. So along Karakoram Highway, You see, it is hundreds of kilometers long, 900 kilometers long, starting from the low point. And some landslide areas are very long and they are very complex and very complicated. Some areas are kilometers and kilometers long, and uh, the sliding takes place in long reaches there. In 2005, on October 8th, when we have a devastating earthquake in the northern part, Kashmir part of Pakistan, many cities were shaken there, and there was a lot of devastation on the slopes in particular. The structures which were present on the slope, they suffered a lot of damage. And you can see a site in Muzaffarabad area, and here you can see some small vehicles, and you see here it is all, the road is almost damaged. Landsliding is not only a local phenomenon, it is an international phenomenon. Wherever we have sloping ground and we have weak formations and the suitable triggering factors, sliding will take place. In the left slide, you see in Taiwan, freeway number 3, the whole system of freeways that is under a big mass of slid mountain. And here in Arizona, Bitter Springs landslide area, a lot of movement has taken place down the valley. In USA, there's a notorious long landslide region called Devil's Slide area. It's very long, kilometers and kilometers in California, and it is along the coastline, Pacific. And in these two slides, you can see some areas marking the trajectory, the zone covered in the slide. And here you see this is also part of the Devil's Landslide. So for civil engineering purposes, this slide has been stabilized at different places using different techniques. If we look at the global index of fatality of landslide globally, we can very easily see that here, this is Asia, this is India, this is Pakistan, and here you see.
Sohail, can I stop you for a second?
Yeah, sure.
But this is a general announcement for everybody that this webinar is connected with Pakistan Engineering Council also. We have to follow their rules very strictly. Those who have to earn CPD points from this lecture, I am again reminding them that they must switch on their video. This is a rule which very strictly PEC is going to follow, and they have asked us to follow the rules. So please switch on your videos who have officially registered for this webinar. Thank you very much. Carry on, Sohail.
Okay. So I was talking of the fatality index of landslides globally. You see in the continents of America, certain regions here in Africa, in Europe, but in Asia, this part is really troubled. We have north of India, Nepal is here, and parts of China, and here Malaysia and Far Eastern countries. But let's talk a blow up of our northern part. So here, so we have issues here. So this area is of Karakoram highway ranges, our northern Gilgit-Baltistan areas, and we all know Kashmir, Kohala, Azad Kashmir, etc. Here is a status which was gathered in 2010 comparing the number of fatal landslides in 20 or 25 countries. So Pakistan is number 6 here. The global fatality status, we are number 6. Number 1 is India. China, Nepal, although a small country, you can see it is having very weak rocks and very weak geology. So for that reason, this is a highly seismic, highly landslide area, and a lot of sliding takes place because of seismicity also. But that is only one factor. So just talking of it, that it's not a new issue. It is an old issue. And so many theories have been developed, and so many cases are there in the literature. And every time some new sliding takes place, we have a learning lesson. There are now ways and means, protocols for investigating the landslide, for studying them, for analyzing them, and for giving good solutions. There's a lot of improvement in the design methods, in the construction methodologies, in the mitigative measures, and in the materials also, and the schemes for mitigation that we are using. There is an increased role of instrumentation also in the landslide domain to find out the actual behavior of the ground, which is subject to movement. What happens to it? What kind of movement? What pressures are there? What pore water pressures are there? So landslides are always not because of the natural reasons like heavy rainfalls or snowfall and earthquakes, and you see erosions and the differential temperatures, but also because of the anthropogenic reasons, which are the man-induced region because of our own activity on the planet Earth. We, for the development works, cut sometimes, we place fill loads at places, we blast, we sometimes remove load from the toe of the slopes of mountains, and sometimes make structures and add weight on the heads of the slopes. We devegetate the ground sometimes. So they are the anthropogenic reasons which slowly trigger the landslides. Now, as we know, there is a pressure and there is a demand that every kind of sloping ground must be utilized for construction activity. Let's talk of muddy area. I would say that most of the stable areas have already been used for construction, and now relatively less stable areas are now openly available for designing and for construction. So that gives an open challenge to the geotechnical engineers and to the civil engineers. Quite recently, my organization, which is NESPAC, was carrying out some consultancy work for C&W department to prepare a landslide hazard zonation map for the whole of Murray. So the idea was to divide Murray town, which is an important town, into 4 or 5 zones having different landslide hazard potential, so that we can identify absolutely safe areas, the areas of average safety and average risk, and the areas which are highly vulnerable to sliding, which may either be abandoned, or one should understand that very costly mitigative measures would be needed there. So that was the purpose. Somehow it was left in the middle, you see, because of certain reasons. Some initial work was done. Now, what is the effect of trapped sepages? They increase the pore water pressure. Whether we're talking of soils or rocks, the water plays havoc. Taking care of water, that is draining the slopes from the surface and from the inside, improves the stability against slidings tremendously at relatively little expense. If there are excessive movements because of certain reasons, of course, that will result into deformation and sliding, and a lot of loss to the property and to the lives could be there. Let's have a look at different types of landslides which we come across in our practice. One is the rotational system, in which the failing mass shown in figure A has underlying as either a circular or a part of a circle or a curvilinear surface in which some rotation is there. Material moves from here, this head scarp, and accumulates here, causing some bulging and flows down. And in contrast, there could be a planar translational sliding also, depends on the materials, like this, a plane surface. The deep rotational failures are a characteristic of cohesive soil. More the cohesion, the more will be the rotational tendency. The materials which are having very little cohesion and predominantly higher angle of internal friction, they tend to have translational failures which are generally not deep-seated, the frictional materials. So similarly, if we have rocks there, in figure C, you can see, so blocks disintegrating because of the weathering action. Here, steeper slope, rock at steeper slope, falling down by disintegration. This is rock fall. But while falling, if the rock fragments turn also, you see, they topple also. So this is toppling. Debris flow, in which the random material with high moisture will tend to flow. You see, literally flow. And there could be avalanche also, debris avalanche, high speed flow. Mainly in avalanche, we have snow component. That could be earth flow, fine grained soil. Between debris and earth flow or mud flow, the main difference is that debris has coarser fragments, high moisture, but in earth flow, we have finer fragments and high moisture. But they tend to flow, both have kind of tend to flow. In another situation, there is a slow movement. Slow movement, it could be even at flatter slopes, relatively flatter slopes, this is called creep. Slow movement goes on taking place. So this means that sliding has different speeds. Depending on the situation, it has different speed. Here you see almost horizontal ground in the last figure at the bottom J, but due to earthquake, spreading will take place. There's another term called solifluction, which is a gradual movement or mass wasting in wet soil because of freeze-thaw activity, solifluction. So here you see the movements of sliding and varying in speed from left to being slowest to the right being fastest. So solifluction and creep slow, slumping after it. Here, lahar and mud flows. The volcanic material when it flows with high moisture, that is called lahar. Lahar, and this is a volcano here. Debris flow, material containing coarser fragment but high moisture. And here we have fast movements in rock slides, rock falls, and sometimes rock avalanches. Avalanches are very high speed phenomena. There's a view of the solifluction. You can see it's a slow movement. Snow and ice, in snow and ice, this is primarily it takes place. Some commentary on very general remedial measures. One is that if this is the original slope, very simple, flatten it. It will make it more stable. Secondly, if this is the slope angle, add fill to make a flatter slope. This will again be stable because we have added weight close to the toe. Whenever we add weight at the toe, we stabilize the slope. Whenever we remove weight from the head, we stabilize the slope. And whenever we do reverse, that is whenever we add weight here and whenever we remove weight from the toe, we destabilize the slope. This is a very common principle and which should be kept in mind. Whenever we take care of drainage, whether surface or subsurface, we stabilize the slope. Whenever we close our eyes on the drainage issues, as is in Murray, the controlling department, they have closed their eyes. They don't even keep the open drains open. You see, it's a very simple thing. If you keep the drains, open drains running, naliyan, the open drains, if they're kept open and running, they will be draining water and they will improve the stability of the slopes. Anyway, this is regarding the care to be taken by the concerned department in the maintenance, in the operation and maintenance business. So similarly, there is another kind of activity which we can do to impart stability to slopes. One is benching, provide a cut, horizontal cut called bench in the slope. And if we provide a kind of embankment or add weight at the toe, this is called berm. So there is a subtle difference between berm and bench, and people have been using these, engineers have been using these words. You see, invariably one word for the other. You see, they cannot be understand to mean the same thing. Provision of drains in situ within the body of the slope, or say for hillock, or for that purpose even mountain. So we have been doing this very often in the areas where we have to give stability, provide horizontal drains and sometimes vertical drains from which the water can be pumped out. Sometimes you see a combination of inclined and horizontal drain. The prime objective is to make the water move out of the slope. That will give it stability because that will reduce the pore water pressure. So of course, when we provide this kind of drain, a sloping drain, chimney drain, we have to use the principles of filter design, and you can see here, geotextiles is also used there. Little commentary on the role of the trees and vegetation on the slopes. As you can see, in the upper part of the figure, there is a slope, there is no vegetation.
So
And
here you have a question on the board.
okay, let me see, just a minute.
The question is, can we stabilize the slope by using some kind of vegetation in alluvial soils? Can it further enhance the stability?
Well, the vegetation will generally improve depending upon the depth of the penetration of the roots of the vegetation. Stability only to the region up to which the roots have penetrated. Many areas in our northern parts, you see, they have different kinds of mechanism, and where deep-seated failures are likely. The factors of safety for deep failures are very low. So there the vegetation will not be that effective. But in general, you see, in areas in which the slopes are not very steep and where the drainage is taken care of, the vegetation does help. So here you can see the scheme made to tackle an avalanche. On the left side, you see a structure made on the roadway to secure the road, and avalanche or any slide for that purpose can just cross over it. This is a good way. And here you can see this tunnels have been made, and any sliding can take place on the roof. This is one good way. In Murray Kohala area, I just had some pictures to show you that providing gabion and masonry retaining walls. On the left-hand side is a gabion, wire created stones is gabion. In steps, these kind of walls having very wide base. As a rule of thumb, the base width could be as much as at least 70% of the height of the wall. So that gives a reasonable stability, but the base of the wall must be sited on a stable surface underneath. If it is already placed on a sliding mass, then it will never gain stability. So if you have seen in Murray area that by roadside there are several walls which have slid down over time, the simple reason is that they were placed, their bases were placed in unstable mass. So we have to have their placement in the stable mass. If that is very deep, that is another question. You see, that's another story. Then we can think of some other solution if going that deep with this system is not possible. So here you see a different kind of wall. You can see a kind of a drain here in retaining wall. This is called a step drain, a cascade drain, to drain the water from the upslopes to downslope areas. So these kinds of drains are very effective. And whenever we have to make a retaining wall, we must provide some holes in the walls. They're called weep holes because water flowing along paths of least resistance in sloping grounds, it tends to find its way and then when there's a wall, it will stop, and we start building up pore water pressure, reducing the effective shearing strength of the soil. So the effective way is to relieve the pore water pressure by providing holes, weep holes. And here, a view of different locations of Islamabad Murray dual carriageway, the new road which is built on the right side of the mountain. The old road is on the left side of the mountain. So at different locations, you can see these retention walls are there to take care of small slides. Let's have a small overview of the general remedial measures for a variety of situations. As I've earlier said, a typical landslide after its study will require certain specific measures. But we must know that what are the underlying causes. First of all, that is important. So here you see that if this is the sliding surface, partly curvilinear and then kind of horizontal, providing piles or some shafts at the toe will give a stability against sliding in this direction. So similarly here you see it's a slope with a lot of unstable mass on it going down, and it has underneath firm stratum. So we can provide for making structure or for giving stability a network of small diapiles, 4 to 6 inches piles. They are typically, they're called micropiles. So network of micropiles is called a reticulated micropile system. This kind of system is used in many other applications also, but in many countries in Europe, I know at least, it has been used excessively, not only for giving stability against sliding, but also to give stability to the old archaeological historical structures. Micropiling has been very common. And here you see at the bottom, the third picture, well, where is the arrow? Yeah. Here you see stable unreinforced slope will require a flatter angle. If we provide reinforcement, we can reduce the quantity of earth material with the reinforcement. Plus, the reinforcement will give it further strength so that this kind of failure tendency will be covered, will be blocked. If we provide deep anchors, deep enough to go beyond the theoretical failure surface, here, this is called the bonded length, and here the anchor will remain unbonded, so it can derive strength from the bond developed in this stable zone, and a number of such anchors can be provided to hold the ground. Generally, they are provided in rock formation, and if you have visited the Bela Dam and above Power House, there is a hillock which had started vibrating immediately after the project went into operation. So it has been stabilized with anchors and bolts. Here you see the stabilized system with anchors.
So here you have a question on the board and a comment.
Yeah. Please, yeah, can you read that for me?
Can we stabilize the slope by using mechanically stabilized earth wall, MSE walls, instead of accumulation of weight at the toe?
So going back here, this is a mechanically stabilized earth. This is one system of mechanically stabilized earth in which we have used reinforcement, you see. So there are many types of MSE walls. This is also an MSE wall. But MSE wall, you see, will require its construction itself. You see, it is fill, it will require its construction. And behind that is the unstable formation, which has to be stopped. Yes, the reinforced earth or mechanically stabilized earth construction has a lot of scope to give stability in the sloping grounds. Yeah. It's all right. Any other question was also there, or some comment is also there, Tahir Saab? Hello?
There is a question. There is a question from engineer Siraj Ahmed.
Yeah.
Why we use sweep holes in the retaining walls? Kindly explain and define actual effect of sweep holes on retaining wall.
It is water which keeps moving in sloping ground from one place to the other, and even from the distant source sometimes. Like electric current, water also in the ground follows the path of least resistance. There is not a well-defined path. The ground which appears dry during construction may become wet in certain season. And when the ground gets wet, it loses its strength and tends to put more pressure, you see, onto the ball, more than it was designed. So the prime aim is to drain the water so that the effective strength of the system remains intact. So here you see applications of soil nails. The prime aim is that in the lower diagram that we provide nailing beyond the theoretical failure surface. And here you see a railway line or a roadway, even that can run. And here you see short-gated faces with nails. So they are all the means to, this is the soil nail reinforced slope. So here I would like to show you, actually I'll narrate this case history in a bit detail at the end of the end part of the lecture. But here this is a figure which has been obtained from Jika Gali car parking plaza project, which was never possible to be constructed because of sliding there. But you can see a 12 or 13 story structure originally planned to be provided on the slope, and this was secured on, you can see piles here. Can you see black vertical lines piles, right? This was the original design. This was the original design. But due to some unpleasant events, unscrupulous construction practices, no care of water during heavy rainfall, heavy excavation during heavy rainfall at the toe, things went wrong. And the plaza was abandoned. But later on, when some mitigative measures were being planned and being considered, then one of the measures, which was although not adopted because of very high cost, was that we can stabilize this slope by providing large diameter shafts and tied back with red tie-back anchors, and this to be provided at a number of places along the slope as we go down. I just want to show that this kind of arrangement is also used sometime, but this is very costly. I know that I showed you the images of that Californian devil slide in USA. Some parts of that notorious devil slide have been stabilized with this technology. And if the design is appropriate and strong enough and sound enough, we can even build a structure later on these kinds of pile anchored systems. So in Jikakali, basically there was a combination of reinforced earth and large diameter piles provided at the toe, which gave stability to the mountain. And here you can see the construction of reinforced earth. So this is partly also an answer to the earlier question that can we use the mechanically stabilized earth to stabilize the landslide? Yes, as we have done here. So here you can see that in this sketch, in this picture, this is the mountain, and here this mass, gray color, upper part is reinforced and the lower part, to save money, was kept unreinforced. And close to toe here, on this side, where there were heavy inflows within ground, large walls of large diameter, 4 feet diameter, and about something like 50, 60 feet long or even more piles were provided. After construction, you can see the finished phase of this reinforced earth system at Jika Gully. You can see here. So this is a reinforced path. This is supposed to grow vegetation in due course of time, provided its maintenance is also done by the concerned staff. You have some signs of vegetation here, but you see it requires maintenance, because if there is some kind of erosion of the sweet soil, which is present on the top right under the mesh which is covering this slope, so if that gets slightly eroded, you see it has to be made up. And the lower part is unreinforced, and whenever there is some bench here, wherever there is a bench here, there's a drain running also there. So that gives stability. The drainage of the slopes is important. While I'm discussing various possible means which can be used to stabilize slides, I would also like to emphasize that in this business, engineers, whatever they do, there are a variety of combination and a lot of money is involved also. So what the engineers do is that they tend to reduce the risk from a high risk, which was before construction, to a lower value. It could be further lowered at the expense of very high cost. So what is done is that in landslide projects, it is accepted that some little risk will be left, and that will be taken care of by periodic maintenance and inspection. No sane engineer would go to reduce the risk factor to so-called zero in this kind of work. I think this is also true in other branches in civil engineering, like in flood management, in design against earthquakes, design for tornadoes and hurricanes. We accept certain level of risk, and then we design for that. So similarly in landslides. And here, this is a trade-off between risk and cost. If we incur less cost, this purple is for cost, we have high risk, but if we go on increasing the amount of money on designing and providing good mitigative measures to arrest landslide, then the risk factor will be reduced to a low value. That very low risk can be effectively taken care of by a system of periodic maintenance and inspection. So this is recognized the world over. And in Pakistan also, we are going with the same system, because otherwise the landslide mitigative measures would become very, very expensive. So is there some question there till now? Any further question? No?
No question yet.
Okay. So I go ahead.
Please go ahead.
Like in other civil engineering works, whenever we have to design, whether on flat or on sloping ground, we have to have some geotechnical investigation, some studies. So similarly, on a landslide area, on a sloping ground also, we have a system, a protocol. First of all, our reconnaissance is carried out, and it is supported with satellite imageries, GIS studies, then some physical studies of the site. Topo survey is very important, and then actual drilling, field testing, some geophysical surveys like seismic refraction surveys, etc. Some appropriate laboratory testing to find out the index properties and the shearing strength attributes. And one important thing is that now we have been using also this practice here in Pakistan on landslide areas, that we instrument them and monitor them for a sufficiently long period. In my experience, we have been monitoring such slopes which are instrumented for 12 to 18 months in general. That's a reasonable period in which we covered, if not one, then two wet seasons also. And we see that what is the order and what is the trend of movements and what is the trend of accumulation of pore water pressure during the rainy seasons, or when it is dry at the site, but it becomes wet at a distant location and sepages travel towards the site. So the piezometric observations are there quite helpful. And we also want to know from such observations that up to how much depth is involved in movement, because that is very much important in designing the landsliding mitigating measures. If only 10 meters is involved, or it is 30 meters of mass which is involved. So that is done by installing extensometers, a kind of instrument which records movement in the ground. Where the movement stops, then there is an indication that below this, the sliding is not, or creeping is not taking place. So similarly, inclination or tilt of the ground is also measured by inclinometer. So there are various instruments. I'll give a brief overview of that. I would also like to emphasize that landslides is such an area in civil engineering in which there is a lot of geological input in real sense of the word. If the geology of the area in which we have to study, analyze and design measures for landsliding control, if geology is not captured properly by very expert geologists, if the cross sections are incorrect, if the geological maps are incorrect, then the whole exercise may go futile. Talking of the slope stability measures, when we have to design a measure to control a landslide, we have to carry out the stability studies. That how much unstable it is, how much mass is involved, and then decisions are taken that what should be done. So there are various methods to ascertain the stability. As for general slopes, for landslides also, the very well conventional, time-tested, recognized method is using limit equilibrium method, in which we establish the equilibrium of either forces or moments. And the sliding mass in general is divided into wedges, into slices to carry out the analysis. On the other hand, there are now some later methods with the finite element and finite difference methods also, which are involved now. And they're said to be very accurate too, and they fit into a variety of geometric conditions. And when we have to find out the behavior of the slopes under earthquake, it becomes important to carry out a dynamic analysis and to find out deformations. Sometimes it so happens that when we have to see the stability of the slope by static methods using limit equilibrium approach, we have to incorporate the effect of the earthquakes by equivalent pseudostatic force. So that is called pseudostatic analysis, in which we incorporate the effect of earthquake by an equivalent horizontal force. But the results of pseudostatic analysis, in our experience worldwide, are not considered to be that reliable. And now it has been established that even if the pseudostatic analysis give low safety factor like 0.7 or 0.8, and if the dynamic analysis on such slopes give the indication that the deformations under earthquakes will not be excessive, then the low safety factor of pseudostatic analysis on such slopes are not given any importance. So this is the trend and a shift in the thinking in the profession. So in small words, stabilizing forces over the destabilizing forces or moments is the factor of safety. The factor of safety has to have a reasonable value, like a value typically of 1.5 in static conditions, and the static loads is considered reasonable during the performance of the structure, and under special conditions of earthquake loading, factor of safety of 1.1 as the ratio of the forces or moments is acceptable. Generally, this is in the general analysis. So for methods of analysis, they used to be carried out by hands. The various methods, longhand methods to find out the stability of slope, methods of slices, There have been Bishop's method, there have been Price and Morgenstern methods, Jumbo's method, and many other authors that have done a lot of work. There is a difference between them on the basis of the difference in the assumptions that they make. So here you see, if it's a slope, it is divided. If we consider this slide, we can define a plane and find what is the factor of safety of that plane. And we divide the slope into slices, into pieces. And the weight of each slice component, you see, this weight and can be divided into two parts. One is, you see, normal to the surface, and other facilitating sliding. So similarly, you can see here uh, at the sliding surface, one of the slides, it shows the shearing resistance upward and the normal resistance because of the weight, right? So taking moment, it's very common to take moment about any point you see. Like one can take a moment about this point or moment about this point, or and find out the equilibrium, and that's how the factor of safety is calculated. So this was true for the longhand methods, and later the numerical methods and the computer models and some softwares are used for limit equilibrium analysis, like slope GeoStudio is very common. So here now it's possible to have a grid of factors of safety, grids of, sorry, centers of circles having different radii, and then to analyze the slope for a number of circles. And
Well, we have a question.
yeah, please.
The question has been asked by engineer Siraj Ahmed.
Mhm.
What precautionary measures are taken due to landslides when groundwater flow in speed and gradually increased? Kindly explain.
We in a landslide area should lay special emphasis on controlling subsurface drainages. And in some areas where this situation is taking place, we have to have a system of internal drains, like I showed, horizontal drains, a system of vertical drains in which the water has to be pumped out, a system of what you can say, French drains, you see, at places which should be able to drain the water out of the slope longitudinally. So it is a combination of the drainage system and also, in addition, the surface drains, looking at the flow pattern and on the topography of the area. The surface drains have to be designed by dividing the area into different uh, rain catchment areas, so that when rain water gets accumulates, uh, that this part gets drained in this drain, this part in this, and like this, primary drain, secondary drain. So it has to be designed like that. And in addition, sometimes when more movement is expected, uh, convex upward walls are also constructed on the slope. You see, can you conceive what I'm saying? Uh, kind of walls which have convex face upward, looking up the slope. If we provide at different places on the slope, they will tend to put brake on the sliding movement. But draining water out, there are many methods, as I've told to you, and these are what we are practicing. Like I talked of Jika Gully, I can talk of Devil Landslide, I can talk of other landslides where we have worked effectively. We have been using these methods, and they are proving to be very effective. I remember a few years back, there was some sliding at Bansra Gully, and there, simple horizontal drains and letting the water out, stabilize it just by providing drainage. No other measure was provided. Just a small notion to clarify for those young engineers who should further get their concepts cleared, that what is this factor of safety in limit equilibrium. It's a planar sliding surface I have shown here, not a circular or a curvilinear surface. So you can see here, this is the expected sliding surface, and this mass could slide. So this will go this way, and a resistance along this plane will be created this way. So restoring forces or moments over disturbing forces or moments.
So here I missed one question, please excuse me. There is
Yeah,
another question.
yeah,
This is
please.
from this is from Muhammad Imran Chaudhary. He's asking, does the landslides is quite common in stratified rock strata?
In which strata?
Rocky
Sorry, in which
strata.
strata? In
Rocky
rocky.
strata.
Yeah, yeah. On Karakoram highway, we have all rocks. And it doesn't mean that even if we have igneous rocks, very hard rocks, sliding will not take place. Sliding will take place because the mechanism of sliding in rocks is different from the mechanism of sliding in soils. There are joints, multiple joints, because of the very formation of rock in different direction. There are bedding planes, their inclination. So sliding in rocks does take place along those joints and along those bedding planes. And we have to sometimes even to provide a vertical face during excavation in rock, we have to bolt those faces sometimes. You see, it could be so serious, even in igneous rock. I've seen in Makkah, I remember once that for an excavation, they had made vertical cut in igneous rock and then they had bolted that so that the big fragments and big chunks of rock should not fall down into the excavation. Here, I just want to show you this slide of Mother and Child Care Hospital in Murray. It is still in the process of construction. Its piling work is nearing completion. So this is a unique project in which the area lies under General Bus Stand area. I think you can conceive of this site. So as you see the geology, the pinkish material is shale and the bluish material is sandstone. So wherever there is sandstone bed, it gives more stability, is a stronger medium. Shale is a weaker, relatively weaker rock. And very interestingly, this is what we call favorable inclination of the beds. You see, load is coming from here. The sliding will not take place downwards. You see, the sliding tendency of this ground is being inhibited by the strong holding beds of sandstone. So you can see interestingly that if you have a look at the general slope of the area above sandstone is flat, but when there is sandstone inclusion, it becomes steep. So nature has given stability by steepening the system itself because of the inclusion of the stronger rock. So the uniqueness in this project is that you can see this is a failure plane, and along the failure plane, the factor of safety has been analyzed as 1.96. Basically, it was found that this area is unstable from landsliding potential point of view, but a hospital building was to be provided. So it was decided that we can design such piles, such large dia piles in sufficient number that did not only give stability to the area against sliding, but would also support the loads of the structure, which is a sensitive hospital building. So this has been achieved. The two purposes have been achieved. The area has been stabilized, ground has been stabilized so that nothing will happen. In the event of a landslide, the forces will be taken care of by the large diameter piles, and the building load on the building in static and in earthquake condition will be taken well by these large diameter piles. So as I was talking about the limit equilibrium method, so it is applied in two ways. One famous terminology is called back analysis, which we carried out when we see that a sliding has taken place at a site and there are indication of the head scarp. One can see with the naked eye that this is the head, the start of the slide, and this is the toe, the foot of the slide. So having known those 2 points, one can define the trajectory of the slide. A kinematical possible failure surface can be developed. So this is how we can define the route of the slide, knowing the 2 points at the site, assuming that to be circular. So that is a very good effective way. And this is how we define the slide trajectory at Jikagali, because the sliding had taken place there and we could find out that it started from here. We found out by observation and by topo survey the zone of accumulation, and we could find out that this is the sliding mass which has slid down. Now fixing a factor of safety of 1, because factor of safety of 1 is just that factor of safety which is responsible to give equilibrium. The disturbing forces are just equal to what you call stabilizing forces. And even if theoretically 0.1% disturbing forces beyond that can trigger landslide. So factor of safety 1 means we are just on the threshold of stability. If we back work the shearing strength parameters in our analysis by repeated trials and iterations, the C value, cohesion value, the phi value, the angle of internal friction value for a factor of safety of 1 in a landslide area. So even without laboratory testing, with fair degree of accuracy, we'll be able to find out the shearing strength parameters responsible during sliding. So this is called back analysis, that you define the trajectory of the slide at the area, at the site, carry out iterations for a factor of safety of 1, and find out the responsible shearing strength parameters during failure. As landslide area, which may be stable today, may become unstable in future because of the change in the geo-environmental conditions. What could those be? One is moisture, other could be earthquake, the natural factors. And third reason could be the anthropogenic reasons. If some excavations are done close to toe of the slope, so much additional weight is put on the head that the slope cannot take place, can take it effectively, or some wrong activity on the slope itself. So this is important to know the weight, to find out the weight of the failing mass, because it is the weight of the lateral mass, lateral force will be generated by the weight during sliding that we have to consider while designing the mitigative measures. Here another slide just to show you again the views of the slides. I want to show you that what is meant by head. This is the head, main scarp, this vertical face, this is the minor secondary scarp, and you have some slump blocks here, deranged forest, see, topsy-turvy trees, ponded water, transverse fissures, and these are transverse ridges. I was calling zone of accumulation. This is the toe, the foot of the mountain, and some other fissures also, radial fissures, etc. This is what happens in a circular. This is close to a circular failure. Now, that was the back analysis. What about the routine stability analysis? In routine stability analysis, we have the geometry of a slope. We carry out some field and laboratory tests, and we find out the appropriate controlling shearing strength parameters, and then we run limit equilibrium analysis or finite element analysis, whatever has to be done. We find out the factor of safety, and we calculate that what is the lowest factor of safety for which surface. So the weight of the soil within that surface, which is generating the minimum factor of safety, is the weight of the sliding mass. If we have to design a restraining measure, that measure should be able, that restraining wall or piles or whatever, should be able to take the lateral thrust of that much sliding mass, which was corresponding to the minimum factor of safety. So then it will be easy to design the mitigative measures. So we carry out in routine practice both static and pseudostatic analysis by same method. And as I told you, in contrast to limit equilibrium method, now finite element methods are also alternative approaches, and they are considered to be accurate, versatile, and a fewer assumptions regarding the failure. But you see, many engineers, even to date, consider them to be a bit cumbersome, and you see, they don't want to go into numerical modeling. And so that's why the state of the art, I would say, still in the profession in landsliding business is limit equilibrium method. Even today, its results are considered fantastically true, and it is more understood by people. The finite element is more software oriented, and one main objection on using such methods is that such methods require accurate determination of the ground properties in large number. Lot of soil investigation and lot of realistic laboratory testing and lot of representative soil and rock parameters have to be there. So just comparing. In finite element method, you can see the failure surfaces shown by distortion, and distortions do take place where the shearing strength of the medium are a minimum. You can see here in three situations depict different ground shearing strength properties. So you can see a very deep, less deep, and relatively shallow. Here, the cohesion value in the upper A part, I presume, would be higher, would be the highest here, and it would be the lowest here. So, just juxtaposing slope with finite element analysis and a slope with routine limit equilibrium failure surface analysis. So some studies have been carried out, and the results are quite comparable. I would say the results are quite comparable. So whatever one wants to do, both are acceptable in profession. About dynamic analysis, when we have earthquake, like in our northern part of Pakistan, we have a lot of seismic activity. So in earthquake-prone areas, we are more concerned, in addition to the sliding stability, about the deformation also. Unfortunately, the methods of limit equilibrium analysis, they lend us only a pseudostatic method in which we approximate the earthquake forces with equivalent equivalent static forces. But that leads to a factor of safety which is considered doubtful in the profession. Even the value which is less than 1 is not considered, acceptable by top experts. And we always go for such cases for full-fledged dynamic analysis, and there are many methods for dynamic analysis. Sarma's method is very popular, and not only do we use on computer, some shortcuts for longhand evaluations of Sarma's methods are also available, in which one gets a fair idea of the deformations which can take place. If they're acceptable, fine. If they're not acceptable, one can take measures to control the deformation by some retention measures, by proper mitigative measures. Yeah. So, any question up to on this topic? Nothing? Right, there's no further question?
Is your lecture finished now? So far
No.
we have. Okay, you carry on. No. If there is a question, I will let you know.
Please do let me know. It is about 40 minutes past 3 p.m. Up to how much time I should keep delivering?
Well, as you told us that it would be about 90 minutes lecture, so I think you still have 15 to 20 minutes more.
Okay, thank you. So I'll have to go into brevity. Okay. Just giving you glimpses because I want to make you aware of many important things related to landslides. As I told you, now the profession of civil engineering is shifting a lot towards performance monitoring. It is a performance-based design which is getting more importance, you see, than our conventional design. So similarly, landslide, we ought to see the performance of the slopes. How do they perform? Not only to design the mitigative measures, but also after having designed the mitigative measure, how they are behaving. So that adds to our professional knowledge and also enables us to design the measures symptomatically according to the symptom. Where there is some problem, we provide the mitigation measure. Where there is no problem, let it go. So a variety of equipments or instrumentations which are done are listed here. Major types are, one is extensometer to find out the deformation, the movement, extension within the ground. Inclinometer, these lead us to find out the inclination of the ground at any depth. Settlement and strain gauges are generally, you see, applied at any level up to which they can be embedded, and settlement markers are normally placed on the surface in the form of any marker. Either it could be a small concrete block embedded with a metal pin on its top or some other marker. Pressure cells embedded within the ground allow us to find out the ground pressure. Piezometers allow us to find out the water pressure, the pore water pressure, and they are very useful sometimes because we sometimes think that the slopes are dry and there's no issue, but they become very wet during wet season. The pressure gauges, the accelegrams record the acceleration during vibration or during seismic movement, vibrometers, the extent of vibrations, the crack meters to measure the depth of cracks in rocks and in concrete works primarily. So sometimes the readings of some of the instruments they look to be odd. So I've just added here that every reading should be taken, and if one finds some doubt, the reading should be repeated. And the higher the susceptibility of movement of the ground, the closer should be the frequency of observations. I mean, if some movement is taking place, daily readings should be taken, you see, no way, maybe 2 times a day. If the movements are very little, then maybe once a week, or maybe one reading after 2 weeks. So here you see one type of modern extensometer called magnetic probe extensometer. I just wanted to share with you that if you look at this figure, this one, there is a PVC casing driven in the ground in a borehole. Borehole is made with a casing, and you can see here 1, 2, 3. These are the embedded spider magnets in the ground. And there's another casing here, this one, outer wall, and within the casing, a sensor, a probe, also called torpedo, that can slide up and down. And if there is a relative movement or settlement of this magnetic probe extensometers, it will be readily picked by the transducer or by the sensor here. So this is how these sensitive equipments operate. And we can, if we have these installed these at different depths in the ground, in the borehole, we can find out that up to what depth the movement is taking place, and after which depth there is no sign of any movement or settlement or deformation in the magnetic probe extensometer. There's no change in the reading. So this is how we capture from this the total depth of movement involved in the ground by extensometers. So there is another type of equipment, inclinometers, which gives the indication of the inclination by measuring the XY values. Piezometers, in which we measure the pore water pressure. Very important to find the water pressure, the pore water pressure. We use in our analysis also. So many kinds of piezometers. Here I show you a plot of the extensometer actually recorded at Mother and Child Care Hospital, whose picture I was showing you earlier. So this is a plot between depth and time. The interval of readings is about something like 7-8 days, a week, something roughly a week on the horizontal axis. On the vertical axis is shown in meters. I think it should have been shown in millimeters for more clarity. Anyway, you can see that there is, except in the initial few readings, it is almost stable, you see, afterwards. So this is a plot of about 6-7 months. So there is no movement recorded, significant movement recorded at this particular location of borehole 14. So very good. This is how they give us the indication of movement. And if you want to look at the inclinometer reading, a plot with depth of the lateral movement. So you can see some lateral movements. You see the inclination of the line itself indicates some lateral movements are there in millimeters, right? -4, this is 0. So from datum 0, well, it could be around 0. So you can say that about at 14, 15 meter depth, the movement, the inclined movement stops in this inclinometer location. I would also like to share with you one important field in landslide studies, which is getting international recognition. That is the development landslide hazard zonation maps. As I told you that I was myself involved a few years back on a very ambitious project ordered by the then Chief Minister of Punjab. He was very keen to develop Murray. So it was decided in a very big meeting that we should have a full-fledged landslide hazard zonation map of Murray area on the pattern of what is being done by other countries where a lot of seismic activity and understanding of the same is there. A lot of landslide activity is there. So I would just like to show you that for a typical area, there are various factors which are involved in finally getting the landslide hazard zonation map. Several factors are involved. Before we arrive at the landslide hazard zonation map, those factors are, you can see here, the elevation. It's mapped here for the area. The slopes with color code, you can see, this is exactly what we had started doing in Murray. Aspect map, the direction of compass, you see, slope towards the compass, curvature map, seismic hazard map. You can see red areas, high seismic hazard here, structure map, the structure of the rocks and the ground, rainfall intensity map, because if the area is relatively unstable, but rainfall is scarce, so it will not be that serious compared to the area of high rainfall. So drainage map, if the drainage is good, but the area is less stable, even then it will be reasonable. So NDVI map. So you can see that cumulatively, on the basis of these 9-10 factors, a landslide hazard zonation map has been plotted here for that particular site. And you can see here, less than 25%, 26 to 45 moderate, very high, red areas are very high, you see, very high hazard, high, moderate, and these areas carry low hazard. So this is how, this is the purpose, you see, because in an area which is a landslide prone area and the landsliding potential is spread erratically, we should be able to find out, particularly after that big Kashmir earthquake, we should be able to find out the areas which are relatively safe, where we can allow general construction with little expense for mitigation, and the areas which should not be used for construction at all. Some areas will be red areas. Why to carry out construction there? Because a lot of money would be spent. And the areas which are of intermediate hazard, we can spend some money and make them useful, make them usable. So this is another area which is finding its place in the landslide studies. I know that the time is less, but I'll continue up to 4 p.m. I have 10 or 11 minutes left. So first of all, I'd like to quickly show you a few glimpses of a good study carried out some years back to study the landsliding areas and the mitigative measures that were designed along Karakoram Highway. There are some very notorious landslides and some are kilometers and kilometers long in length. Now, as you know, KKH makes a very important route which links Pakistan with China, and it could be a future trade route. And we know nowadays that CPEC project also you see linking with China. So whenever we construct roads and civil engineering works in mountainous areas, we do come across landslides. So the underlying factors are different. What are the main characteristics of Karakoram Highway? We have high mountains, yes, very high, barren, and they're barren, no vegetation. Earlier, somebody questioned about the role of vegetation. To the mountains there are almost devoid of vegetation. And not only mountains are high, quite often the slopes are very steep. So that also adds to instability. And they are subjected to extreme weather conditions. There's snowfall, there are differential temperatures. And as a result, the rocks have become jointed and jointed in due course of time. And the deposits on the steep slopes at places are very unstable. And in addition to that, the construction of Karakoram Highway, which was carried out many years back, was not in a very controlled condition. And that was not very good engineering at the time. I would say the blasting was done there. Blasting is not bad, but if it's done uncontrolled, then it is very bad. If it is done in a controlled way with mitigative measures, then it is reasonably good. But I think the excavation work and the cutting work and the blasting work has been, you see, quite devastating along Karakoram Highway. So with the result that the areas which are prone to landslide, their landsliding potential that once triggered keeps on and on. So it is 16 years old study, but nevertheless, since I was the leader of this team, so I know this thing, and it was of interest to share my personal experience. Total length of KKH is 840 kilometers from Hasnabandal to Khunjarab. And for study, total length to be redesigned was 462 kilometers. So basic purpose of this redesign was to redesign and to consider redesigning for Bhasha Dam project from Havelia to Raikot, 462 kilometers. This is further bifurcated into first part, the length to be widened from Havelia to dam site, 322 kilometers, and the length above the dam site, which has to be realigned and to be put on higher elevation, 140 kilometers. This is not very clear map. I should show you this one. So here you see, if we go back, the study area was Havelia to Raikot, Havelia to dam site and dam site to Raikot. So here you see at the bottom, Havelia, traveling over Karakoram, have many areas, Shinkiari, Balakot, this and that, Thakot, etc., till the point you reach here, the dam site. So this portion, 322 kilometers, was considered for redesigning, for facilitating movement of construction machinery, to widen it sufficiently, stable stretch. And beyond that, you can see a yellowed portion. Yellowed portion is the one which will be submerged, that portion of the Karakoram Highway which will be submerged after construction of Bhasha Dam. It will be submerged in the lake up to this point, Raikot, where there is a bridge. So this yellow part from Bhasha Dam, this is in the lake part, the road had to be lifted up at a higher elevation. So landsliding studies from that angle were important. So the basic underlying requirement was that where the road has to be widened, it must be widened from existing 4.5 meter width to 7 meter width, addition of 2.5 meters to allow for movement of machinery for Bhasha Dam. And in view of future submergence of Karakoram Highway in the reservoir, from dam side to Raikot Bridge, the road has to be lifted and realigned at a higher level. So there was a basic philosophy, a lot of discussion. It was JV, NASPAC AC, and top expert from Kent State University was also there. A Pakistani professor, Professor Dr. Abdul Shakur. He was here in Pakistan during the study phase. And we carried out a number of site visits in addition to the office work and some testing and some laboratory work. So it was decided as a principle that slope movements have the potential to continue despite remedial measures. We should accept this. We should not go for a zero risk situation. That was decided at point number one. Second point this was decided was landslide hazard can only be minimized with remedial measures. Regular maintenance is also essential, so the remainder hazard will be taken care of by regular maintenance, periodic maintenance. It was recognized that the risk will be reduced to such a level that no loss of human life probably could take place. So excavation in the toe of the slope was decided to be avoided in as far as possible, in widening as far as possible. That was the last priority. Don't excavate. I also shared with you, unless it is, you see, unavoidable. Don't excavate in the toe of the slope. Try to provide the widening of the road in landslide areas or in sloping areas on the valley side. Generally, that is better. Most cost-effective solution is desirable, you see. Cost-effective would mean that not only whose capital cost at the time of construction is low, but whose cost over its economical life, like 50 or 60 years on repairs and maintenance, that also combined together will be within limits, total cost. So such factor is called cost-effective. As at some location, it was accepted that the hazard had to be accepted in view of its enormity, because we engineers have to look to the client's requirements also and to the budget constraints also. So some measures which could include stoppage of traffic for some days, maybe like this. Accordingly, mitigative measures have to be planned. So what were the study component for Karakoram Highway at that stage? Reconnaissance, topography, satellite imageries and GIS, detailed geological mapping along the whole hundreds of kilometers, very tough exercise.
So here we have a question.
Yeah, please.
This question has been asked by Asad Iqbal. He's asking, can you briefly describe ground strata in Dam Rycote site?
At the dam axis. Hello.
Hopefully he means that, but he has said Dam Rycote site, Raikot, Rycote site. So maybe
Well, I don't have the geological picture right now, but I have a geological map. You see, just a minute. I don't have a deep drilling record right at Rycote right now. I can share that information. Just a minute. Let me go ahead. Yeah. Here you see, we have, just a minute. This is a Rycote area. So surface geology, we can read from the color code, this dark purple, this limestone and sandstone on this, and then we have blues of two different shades. I'm not good in geology. This is some leucogranite and pluton. You see, it's difficult geological terms. You see, so this is what appears to be here. This is what I'm saying. Some kind of granite work is there, right? I don't have further information on this. So different types of studies you see. Before I finish, I want just to show you 2-3 more slides. One is that there is a very good classification made by Cruden and Warnes on the slope movement systems. Type of movements are divided into 5 types, varying from fall to topple to slide, to spread and flow, right? Now, depending on the type of material, whether rock is involved or coarser material is involved or finer materials is involved, it will be called, in case of fall, rock fall for rock, debris fall for coarser material, and earth fall or mud fall for final material. So similarly for others, like for flow, rock flow, debris flow, earth flow. So this is a very general, big, abbreviated classification made by Cruden and Warnes in 1996. And one slide I want to show you about the speed to capture the concept about the speed at which the sliding takes place. It has been divided by Cruden and Warnes into 7 categories from 1 to 7, from extremely rapid, extremely slow. Extremely rapid would be something like approaching 5 meters per second. And 5 meters per second would be something like 18 kilometers per hour. Is it fast enough? Can anybody comment? Is it fast enough? From the comparison with the car's speed, it is not fast. But from landslide's point of view, it is reasonably fast. And here you see very slow creep. There are creeps, 1.6, 1 or 2 mm per year.
We have a question.
Yeah, please.
This question has been asked by Muhammad Imran Chaudhry.
Yeah.
He's asking, landslides due to volcanic activity are some of the most devastating types. Can we reduce volcanic activity?
Had we been able with civil engineering or with engineering measures to reduce volcanic activity, we could have done that. We have not been, human beings have not been that strong in their knowledge and physical might at the moment to fight against the big forces of nature. We cannot control earthquakes. We cannot control tornadoes and hurricanes. We cannot control volcanic activity at the moment. So here you can see the speeds. You see, it is good not to build, you see, on the crater or near the crater or on the downslope of the crater of a volcano. This is a one good measure because that is a red area. So here, if we look at the speed of avalanche and compare that with the general maximum speed, which is as for the classification given by Cruden, that was 5 meters per second or translated into 18 kilometers per hour. But avalanches, 80 miles per hour they can approach, which is something like more than 120, something 120 kilometers or more like that per hour. One can convert quickly. 80, just a minute, I can make a quick conversion. 80 into 8 divided 5, roughly 128 kilometers per hour. So avalanches should be defined in our northern part. We do at some places, large body of snow and ice sliding swiftly, very fast speed. Steeper slopes tend to continually slow snow because it is steep. So in order the snow to gain stability will slide down and a deep snow layer will form, you see, at the lower elevations normally. So it is said on the basis of studies that avalanche risk of sliding is at its greatest within 24 hours following a snowfall of 12 inches or more. So if there is a snowfall on such peaky steep mountains of 12 inches or more, then the next 24 hours are very vulnerable. One should expect an avalanche. I think time is over. Time is up. I should not consume much time. I'm sorry, I have to finish it, but I think I've been able to give some basic concepts about the study, about analysis, and about mitigation of landslides. Any question? In the end, if somebody is interested, I'm here. Please do ask.
If somebody is interested to ask question on the microphone, please raise your hand. I can allow 5 minutes for question answer session, 5 to 10 minutes. Please raise your hand if you have any question. I'll unmute the mic. So here looks like we have no questions. So
Oh.
thank you. So thank you very much. Huh? Nobody has raised the hand. So thank you very much, Suhail, for a very, very informative and a very good lecture. I think the young engineers must have learned a lot from what you have explained today, and also the senior engineers. So thank you very much. And now I will conclude the proceedings of today after giving you some information. As I said earlier, the next lecture is on 16th June 2020, same time, 1400 hours, that is 2 p.m. Pakistan time. And the topic is earthquake resistant design of RCC buildings, an overview of practicing structural engineer. It's on 16th June, 2 p.m. and the speaker is engineer Rizwan Mirza. In the end, I would again thank everyone who joined us this afternoon from Pakistan and from Australia, and few joined us on Facebook too. And I can't figure out from where they have joined, but from wherever they have joined, uh, I thank them very much, and wish them a good remaining Ramadan. And to the participants, I also wish blessings of Ramadan for the remaining Ramadan. And regarding certificates, there would be two options. One, the participants who are based in Lahore, they can collect the certificates from our office from 13th May, including 13th May. You can collect your certificates from our office in Lahore, which is in 38, Block 1, Sector B1, Township. The address is given on our website. You can check from there. And those who are living out of Lahore, they can contact Mrs. Sadia Naveed. And one option is that we can TCS the certificates through courier mail to you, but in that case, you will have to pay. We will send you the certificates, and when the courier mail will approach you for delivery, at that time, you will pay. So it's up to you. One option is get it from the office, or the second option is if you want somebody is requesting for sending it by courier, then you will have to pay. So after 13th May, you can collect your certificate. And for the speaker, we have a shield. It would be our honor to get it delivered at your home, Suhail. A shield for you. Have you got my message, Suhail?
Yeah, I got your message.
Okay.
With your permission, I will just like to say one line that I am very happy to have the unique honor of being the first lecturer of the online lecture series initiated by Pakistan Society of Engineers. I'm very happy. And it went as a successful experiment too.
Yeah. Actually, this was the point I had written in my notes here, but since you came a bit late, so I started earlier and I could not say it.
Okay.
Anyhow, yeah, it's an honor for you that you are the first speaker who has started in this webinar. So, gentlemen, if let me see if anybody has any questions here or any comment. Okay. So now, thank you very much again for all the participants who are here. It's one lady and all other are the gentlemen. Thank you very much. And on Facebook, we have today we have about 8 or 10 participants. Thank you there also. And please take care. Yeah, one more thing. How long we will continue like this? As I told you in earlier, that it is not knowable how long we will continue like this, but till the circumstances which are prevailing, they continue. We have no option except to go with this option of webinar, and inshallah we will continue it, and we will try to Pakistan Society of Civil Engineers will try to serve you better than its best. So thank you very much. Allah Hafiz.
Thank you very much.